In this video, we're going to work some example problems related to applications of radian measure, specifically calculating the length of a circular arc, as well as calculating the area of a sector within a circle. All right, if the radius of a circle is doubled, how is the length of the arc intercepted by a fixed central angle changed? So when it comes to the arc length of an arc within a circle, you shouldn't have to memorize the radian formula for this. This is just as long as you know what the definition of radians are, then you can get this formula yourself. So you know that the idea is you take any arc length, like arc length of a circle, right? So pick any arc length, say that, okay? So this has length S, and then you could associate with that arc length, if you imagine that the circle is centered at an origin, like an XY coordinate system origin, and then you think about an angle that has vertex at the origin, you can associate with that arc length an angle. Okay, well, if that angle is in radians, then all you're asking is how many radiuses is this arc length? So this is the radius. How many radiuses is this? What does it mean to say when you say like how many? What does that mean? How many radiuses is this arc length? Well, when you think about, if you had 1,000 eggs, and you wanted to know how many cartons of eggs is this? If there were, if a carton, let's say, is a dozen, there's 1,000 eggs or something, and you want to know, okay, how many cartons of eggs is that? What does that mean? Well, you're dividing by 12. You're dividing all of the eggs by 12, and then that gives you how many cartons. If you want to know how many radiuses this is, you're just dividing it by the radius. Like how many radiuses of this circle are contained within this arc length? It's kind of hard to say that because it looks like this arc length is less than the radius. Well, yeah, it probably is. So it's going to be like 0.8 radiuses, but that still makes sense. Okay, and that's what the angle is. An angle in radians is how many radiuses does the angle kind of walk around the circle. But it's you might be saying, well, what circle? Well, it's any circle, because this is normalized as far as radius, so it's the same for any circle, any size circle. Okay, so that's the definition. So that's how you calculate radians, but here we're thinking about how do you calculate the arc length. We'll just multiply both sides by the radius. And that's how you calculate the arc length of a circle. What circle? Well, you specify what the radius. Okay, so if the radius of a circle is doubled, how is the length of the arc intercepted by a fixed central angle changed? Well, okay, what happens if we're not going to change this formula? What happens if we double the radius? Well, we multiply both sides by 2. So the arc length is doubled. If you double the radius, you're going to double the arc length. Radian measure simplifies many formulas, such as the formula for arc length. Give the corresponding formula when theta is measured in degrees instead of radians. Okay, so how could we, what are they asking here? They're asking if you have an angle that intercepts a certain arc length, but that angle is in degrees. What's the formula for calculating the arc length? Well, okay, we can think about it this way. Let's convert this angle to radians and then apply this formula. So if you have an angle theta, and this is in degrees, how do you convert it to radians? Well, we've already worked a bunch of example problems doing this. You say, so this is degrees. You say there's 180 degrees for every pi radians. So what we've got is these cancel, and you've got pi theta over 180. This is in radians. So now we have an angle in radians. Like we haven't changed like the physical nature of this. It's the same angle, it's the same angle measure. We just converted it to radians, right? We haven't changed any of this. So we've got this angle in radians now given by this, and we want to know what the arc length is. Well, we just multiply that times the radius. So S is pi over 180 r theta. Still, it's not that much more complicated, but still, you can see this is definitely simpler. Okay, find the exact length of each arc intercepted by the given central angle. So what is the length of this arc? What is this? S. Well, this is easy. S is equal to r theta. As long as we make sure theta is in radians, it doesn't matter if it's a quadrantal angle, if it's a negative angle, or, well, I mean, if it's a negative angle, I mean, you wouldn't want to specify a negative length. I mean, maybe, but you get the idea. It doesn't matter if it's a quadrantal angle, acute angle, obtuse greater than 270. That doesn't matter. This formula applies in general. If you had an angle that was 700 or 500 something degrees, so it's like 1.5 rotations, let's say, that would be 360 plus 90, so 450. You convert that to radians. What is that telling you? 450 degrees. Let's look at this. 450 degrees in radians. That's 5 pi over 4. If you multiply this times the radius, what is that telling you? The angle in radians is how many radiuses that this angle has like intercepted. You know, it's rotated a certain amount. How many radiuses has it rotated through? Right? The radians is the amount of rotation from an angular perspective, the amount that angle has rotated around any circle. It's normalized for any size circle. So it's how many radiuses has this rotated through about. Radiuses in general, any radius. So if you can think about the arc length of any circle that corresponds to this many rotations, so to look at a specific circle, you just multiply this times the radius of the circle, and that'll be the length of you can think of like a piece of string that you kind of, if you cut this and then made it straight, how long would the piece of string be if you rotated through this circle of radius 4 1.25 times? That's the idea. So this formula applies for any angle in radians. And I guess you could think about a negative length if the problem warrants that. But okay, so S is equal to 4 times pi over 2. We're in radians. So S is equal to 2 pi. You might say 2 pi, that's a full rotation. This doesn't make sense. Yeah, 2 pi is a full rotation if the radius is 1, but the radius is 4 here. The circumference of this circle is 2 pi r. The circumference of this circle is 8 pi. See? And now the units, we don't know the units. Whatever, this could be inches, centimeters, we don't know. Okay, what's this arc length? Well, they already give us the angle in radians, so S is equal to r theta. We see r is 16. That's it. That's simple. That's the radians makes it simple. So 20 pi. 20 pi, the circumference of a circle is just 2 pi. How can it be 20 pi? Well, the radius is 16. Okay, what's the radius of this circle? What is r? Well, we have a length of an arc and the corresponding angle that intercepts that arc. So we've got what we need to calculate r. Divide both sides by theta, and you get what? Remember, radians are unitless. So it's an arc length, 6 pi, that's a length, divided by something unitless is going to give you a length. Radius is a length. So 6 pi over 1 times 4 over 3 pi. This is going to be 2. So r is equal to 8. Okay, what's the radius of this circle? S is equal to r theta, so r is equal to s over theta. S, this arc length, is 14 pi, and it's intercepted by an angle of, in radians, of 7 pi over 4. So this radius is 8. Okay, what is the measure of the central angle here? So we have a radius, we've got an arc length, but we don't know the angle that intercepts that arc length. Well, okay, let's just look at this. The radius is 3, the arc length is 3. What does that mean? We don't even need to use the formula here. How many radiuses is this arc length? It's 1 radius. So this angle intercepts 1 radius. That means the angle is 1 radian, right? That's like the definition of radians. And remember, this is acceptable. I don't have to put, if this was degrees, I would have to put degrees. But I could leave this unitless just like that, or I could write radians, the full word, or just like RAD. Okay, thinking about the definition of radians, how many radiuses is this arc length? Well, if the radius is 10, you've gone 2 radiuses, so theta is going to be 2. But let's do the formula. So we're looking for theta is s divided by r. That's a length divided by length. That's unitless. S is 20, r is 10, so theta is 2. 2 radians. All right, find the area of each sector, of the shown sector. So this area. Now, the formula for the area of a sector in radians, that's something that you could memorize, in my opinion, but not even memorize, but it's so intuitive, you could just derive it wherever you are. And so what I mean is that, so you need to know you have to think about it this way. What's the area of a circle? Everyone knows that formula. It's pi r squared. Now what are the units here? Well, no, pi is not in like radians or anything. Pi is the actual definition of pi here. R is just whatever the length units are. It's whatever you want, pi r squared. So if you're thinking about the area of a sector and you know the angle that corresponds to the sector, then how do you calculate the area of the sector? This should be really intuitive. And it doesn't matter if you're in degrees or any other radians or any other angle. It doesn't matter. It's all the same thing. Okay, if we're in degrees, then all we need to do is divide that angle by 360, and you get like a fraction of between 0 and 1, and it's that fraction of the total area. So if this was in degrees, you would say theta divided by 360 times pi r squared, and that's the area of the sector. Okay, now theta is in degrees here. So how does it work for radians? And does radians simplify? It makes it simpler, apparently. Yeah, it does, and you can see why it does. So same idea, theta in radians divided by what's a full rotation in radians. Okay, so now times pi r squared. The thetas cancel, or the pi's cancel. That's the difference. Nothing cancels here. Here, the pi's cancel, so you get 1/2 theta r squared. That's the area of a sector in radians. Now, if you don't find this that intuitive, then you could just do a Google search for the area of a sector, the formula for the area of a sector. Just make sure you have a good reference. But you just have to keep in mind that in a case like this, the formulas are going to be different depending on if it's radians or degrees, right? Because this is a little different. Not much different, but it's definitely different. Okay, so what is the area of this sector? Well, we need to do a little preliminary work because the inputs here, we've got the radius, but we don't have the theta. So how do we get the theta? Well, we've got the arc length that the theta intercepts, so we could say that. So we know that S is equal to R theta. That relates the radius, the arc length, and the angle. So the theta here is S over R, so that's 2 pi over 6, pi over 3. So there's theta. So the area of the sector then is 1/2, and you just input the theta in radians. This is unitless. Radians is unitless, and we're left with r squared. That's going to be like a distance, like meters squared or inches squared. That makes sense. That's area is in like square inches, or like a length squared. So this is 1/2 times pi over 3 times 36. So you've got, and 6 times 3 is 18. So 6 pi. Okay, what's the area of this sector? You can see it's 3/4 of the area of this circle. Well, what's the area of this circle? We just need the radius. The radius is 10, so 3/4 of pi r squared. But that's why the sector area formula is so intuitive to me, because okay, but if we think about this in terms of the formula, like okay, if this was in degrees, this divided by 360, well, you see what's going to happen is the theta is going to be at 3/4 of 360. It's going to be 270. So 270 divided by 360 is 3/4, and you multiply that times pi times 10 squared. You see? Now we can go ahead and do this calculation more formally. So theta is equal to s over r. So theta is equal to 15 pi over 10. Well, no, this is not going to be 3/4. This is going to be, so divided by 5 is 2, so 3 pi over 2. Yeah, because it's 3/4 of 2 pi, right? 3/2 pi, that's, if you think about 2 pi, that's 3/4 of 2 pi. But when you think about the area of the sector formula, what happens? You've got, in radians, you've got theta divided by 2 pi times pi r squared. So when you do theta here, 3 pi over 2 divided by 2 pi, so 1 over 2 pi, that becomes 3/4 times pi r squared. You see, that's how the formula works out, but we can just go ahead and input this directly into the formula. That's what's nice about the formula. I'm just trying to build your intuition for it here. But so theta is 3 pi over 2, so the area of a sector in radians is 1/2 theta r squared, so 1/2 theta is 3 pi over 2, and then r squared is 100. So (25 times 3), so 75 pi. Okay, find the measure in radians of each central angle. The number inside the sector is the area. So now we've got the area of a sector, we've got a radius, but we want to find what is the corresponding angle. Well, it's just, we go to the area of the sector formula. 1/2 theta r squared. So we just solve for theta. So theta is equal to, it's going to be 2as over r squared, right? Divide both sides by r squared. Divide both sides by 1/2, so that means you're multiplying by 2. And there you go. So 2, the as is 3 square units, divided by the r squared is 4. And so does the units match up? So 2 is just a number. This is length squared, length squared. So yeah, we get unitless. That's what radians are. So 3/2. Okay, now this is it's weird. 3/2 pi, what is this? This isn't 90 degrees, right? This is 90 degrees. So what is 3/2? Not 3/2 pi. What is this? Okay, well, what is in radians? What's the 90-degree angle? That's pi divided by 2. That's like 3.14 divided by 2. So that's, 3 divided by 2 is 1.5, so like 1.55-ish, right? So a little bit less than 1.5 is 3/2. That makes sense. This is exactly 3/2 radians. Okay, here the area of the sector is 1/2 theta r squared. So we're solving for the angle again. So theta is equal to 2as over r squared. 2 times 8 over 16. So 1 radian. Does that make sense? 1 radian. It looks like it's about 1 radian, but okay, if this is 1 radian, then that means this is 4, right? Because it's gone 1 radius. This must be 1 radian. So when you think about the area of a sector, so 1/2 times the radius squared, 1/2 times 16 is 8. There you go. Okay, so same type of problem, but now they're asking for the central angle in degrees. So what do we do here? Well, this is easy. We're going to do exactly what we did in the previous 2 problems, but then we'll just convert the final answer to degrees. Or you could use the formula for the central angle in degrees, but you wouldn't want to do that because they give the area in, well, no, you could do that. 6 pi square units. Yeah, this has nothing to do with degrees or radians. This is like square length. So yeah, I mean, you could use the formula for the area of a sector in degrees, but to me the formula is easier to remember in radians. So let's just solve for this in radians and then just convert it to degrees. So theta is equal to 2as over r squared. So 2, the area is 6 pi over r squared is 36. So theta is pi over 3. Okay, but pi over 3 radians is what in degrees? So you've got pi radians for every 180 degrees. 180 divided by 3 is 60 degrees. So theta is equal to 60 degrees. If you have an area of a sector that's 6 pi square length, whatever, and the corresponding radius is 6 of that same length unit, then the angle intercepted by that creates that sector area must be 60 degrees. Okay, so theta is equal to 2as over r squared. So 2, and this is 96 pi over, well, 12 squared is 144. So let's see. 70 times 2 is 140. That means that this would be 72. So, okay, let's just do 96 divided by 144 is 2/3. So 4 pi over 3. That's this angle. But what is this in degrees? So pi radians for every 180 degrees. 60 times 3 is 180. 60 times 4, 6 times 4 is 24, so 240 degrees.